Okay, so after a long gap, I guess, right? Because you were busy in 4 days, so I think you might have not got any time to look at anything, right? Anyway, so we were looking at discrete log problem, and I think last time I asked you to look at index calculus method as an exercise. I gave it to you, and today I'm going to do. I'm going to look at so. So essentially, last class I told you about two algorithms which can be used to compute discrete log, and of course it's a difficult problem. So essentially, what is a discrete log problem? Uh, so if alpha and beta are given to you, say in integer modulo p or whatever, and alpha is for x equal to beta, so you have to find x, right, in terms of alpha and beta. Okay. So when the structure is discrete, actually, right, it looks like a log, right? So and it is well defined if you take alpha to be a primitive element. Okay. Then it behaves more or less in the same manner as the log function. So since finding discrete log is a difficult problem, Cryptosystem has been built. Especially, I'm going to talk about Elgamal Cryptosystem. And first of all, I'm going to talk about Def-Hellman key exchange, which was the backbone for RSA Cryptosystem in 1977. So I think, yeah, 76, this Cryptosystem, this Def-Hellman key exchange problem was described in terms of discrete log. Since discrete log is a difficult problem, hence the Cryptosystem is secure. So I'm going to talk about key exchange problem, and then I'm going to talk about Elgamal Cryptosystem in general. And then, so basically one can compute discrete log over any finite group, say G. And so one of them is, if you look at any finite field, having certain q number of elements, say, right, where q is a prime power. So you look at all non-zero elements. So as a multiplicative group, all those elements will form a multiplicative group, and you can describe the discrete log problem there. Or, you know, if you take an elliptic curve, so I'm going to talk about elliptic curve, what is elliptic curve, and how the points on the elliptic curve actually forms a group with respect to addition. So you define a special kind of addition between elements, between the points on the elliptic curves, okay? And so essentially, then the discrete log problem becomes, you take a point P, add it certain number of times, say m times P is equal to Q, some other point, because it's a group, so you will fall into the group. So m times P is equal to Q. P and Q are known, finding m is a difficult thing. And so based on that, elliptic curve cryptosystem has been developed. After that, people generalize this idea to hyper-elliptic curve. So what are these elliptic curves? How do you describe them? It's a very beautiful subject. Beautiful mathematics, I would say, and so, dense, of course. So I think many of your, colleagues or peers, they find it difficult to understand when you go into deep. It's not difficult. The only thing is you have to devote more time. And it's such a vast and rich area that a whole course is possible on elliptic curves. It's a beautiful area. So essentially, if you look at parabola, hyperbola, or ellipse, right? So these are the curves which can be parameterized, right? You can find a parametric representation. Like for circle, you have x equal to sine theta cos theta, right? For theta is a parameter, or hyperbola, or all these curves. So these curves where you can do the parameterization are known as curves of genus 0. Genus is a smoothness measurement of the curve. Okay. So when the genus G is 1, it is known as elliptic curve. And when genus G is greater than 1, it is known as hyperelliptic curve. Okay. So this is the basic setting. So I'm going to talk about elliptic curve, how to find this, how to define the addition. I'm going to explain to that thing. So certain geometrical way you can do these things. And in fact, some of your seniors right now working with me on classification of elliptic curves over integer modulo n. So people have not done that work, and they are doing it, and I think they are enjoying it. So they are doing it since last February or something. They obtained few results, and still the work is going on. So I mean, it's not a one-day job, but so these curves could be useful in developing cryptosystems when you develop over rings. Okay. So anyway, so let me talk about start with. So essentially, we are looking at discrete log problem. So when alpha and beta belongs to a group G. Okay. So we can say that it is over in ZP star or whatever, right? Except 0. Anyway, so X we need to find, and we call it X is equal to log of base alpha of beta. This is our discrete log, right? And computing, I already gave you 2 algorithms. So I'm going to describe Def-Hellman key exchange. This is a very beautiful discovery. And just after this discovery in 1976, immediately in 1977, RSA Cryptosystem was formed by Revis, Edelman, and who is the third person? Revis, Shamir, and Edelman. And as you know, Edelman started later on DNA computing. Shamir is also working a lot in biology. And Revis is a professor of mathematics at MIT. Anyway, so Def-Hellman key exchange problem. Let me explain what is this. So normally we, what we do here, how do we exchange keys securely? So either Alice or Bob, you can call Ram or Shyam also, but I am just using whatever term is there, right? Alice or Bob selects a large secure prime P. They select a large prime P, okay, and a primitive root alpha mod P. Alpha is a primitive root. So that means order of alpha is P minus 1, right? That is a primitive root. And then they select a large prime P, and then they select a primitive root alpha. Because then the log is well defined, right? I mean, you know that. Now both P and alpha, they can be made public. So Alice and Bob wants to exchange the key securely, right? How do they do that? So what they do, they select a large prime P and a primitive root alpha, and then P comma alpha is publicly listed. Okay. Next. So P and alpha is known to everyone. Now what Alice does, second step, Alice chooses secret random X, 1 less than equal to X less than equal to P minus 1, right? P minus 2, right? So you select a secret X, and Bob selects a secret random Y. Two numbers X and Y are selected. Alice selects X and Bob selects Y. Then step 3, Alice sends alpha raised for X mod P to Bob. Okay. X is selected by Alice, Y is selected by Bob randomly, right? And then Alice sends alpha raised for X to Bob, and Bob sends alpha raised for Y mod P to Alice. So alpha is known, P is known, right, to everyone, made public. X is selected by Alice and Y is selected by Bob secretly, random number. Alice sends alpha raised for X to Bob, and Bob sends alpha raised for Y to Alice. Okay, mod P. This can be done. Okay. So then, using the messages they receive, they can actually compute the session key. And this happens all the time whenever you are accessing your banking website and so on, because RSA crypto system uses this technology, right? Okay, so session key is established. So what is session key for Alice? Session key is K is equal to, because Alice has alpha raised per Y sent by Bob. Then you raise it to power X mod P. This is the session key for Alice, right? And for Bob, session key will be alpha raised to power X, because Bob has alpha raised to power X, right? Raise it to the power Y, the secret Y. So both have same key, right? Key is same to both of them, right? So basically, once they obtain K, session key, they can, for example, they can use middle of 56 bits out of this K. So basically, so this is used to actually get to transmit secret key, which is used for, say, so AES or DES, right? You use key, right? And the mechanism. So that master key could be, for example, first or middle 56 bits of K. So K is common to both of them, right? They know what is K, right? So take 56 bits or whatever. I'm going to give an example. Middle of the 56 bits of this K will act as a master key for your scheme, whatever AES and DES, right? So that is how you can secretly send the key. Okay. So and the system is secure. Why? Because discrete log problem is difficult to solve, right? Because so now I think this was the key exchange problem. So formally, I can define discrete log. So a multiplicative group, we take G is a multiplicative group, alpha is an element in G, and suppose order of alpha is n. That means you take beta, which is, so alpha generates basically the whole group G. This is nothing but alpha raised for I, such that 0 less than equal to I less than equal to n minus 1. All elements of the group can be generated by alpha. Okay. So question is, find a unique integer A this is symbol for unique integer A less than between A and n minus 1, such that alpha raised to A is equal to beta, and then A is known as discrete log of beta, right? So in general, I mean, whatever you can do over integer modulo P or whatever for a finite group. So there we were taking alpha to be primitive root, right? Here we are taking alpha to be the generator of the group, right? So alpha, order of alpha is n actually, right? So P belongs to this, this group actually, which is, all these powers of alpha. So find a unique integer A. So now you can see that this group, as I mentioned, could be the finite group of multiplicative group of the finite field, right? That you take. All are powers of alpha, if you remember. 0 is there, but you discard 0, non-zero elements will form a multiplicative group. 1, I mean, you saw the table, right? Whenever you are making the table, right? So 1 alpha, alpha square, everything in the power of alpha, you can write, right? So that is the key thing. Or any group for your, So normally, those are the popular groups. So I can now describe Elgamal crypto system. Okay. So it works on discrete log problem in CP star multiplicative. So I think I can write it down. What is Elgamal crypto system? P is a prime. and we make sure that discrete log problem is infeasible in ZP star, right? Alpha is an element in ZP star, fine, and it's a primitive element. So order of alpha is p minus 1. Let p is ZP star, plain text, C is ZP star cross ZP star, and define key k as p alpha a beta, such that beta is congruent to alpha raised to power a mod p. So p, alpha, and beta are public key, and a is a private key. Right. So this is our Elgamal crypto system. So I need to define the encryption rule and decryption rule. So I told you about the key. So key consisting of 4, it's a 4 tuple. So p, alpha, and beta are public key, and a is a private key. Okay. Once you are able to do this, I can define for a particular key, if k is equal to, sorry, p alpha a beta, and for a secret random number x, oh sorry, I will call it here k. Sorry, secret number x. So basically encryption is x comma k. This is your plain text. Okay, is equal to y1 y2. So this is your cipher text. What is y1 y2? Y1 is alpha raised to power k mod p, and y2 is x times beta raised to power k mod p. So in this crypto system, for a given key, so we know that p, alpha, and beta are public key, a is a private key, encryption is x comma k for some plain text x, and k is this key, encryption is y1 y2 pair. That's why it is ZP star cross ZP star, right? So now y1 is alpha raised to power k mod p, and y2 is x times beta raised to power k mod p. Okay. And this is encryption rule. So we need to also give the decryption rule for y1 and y2 in ZP star. Decryption rule dk of y1 y2 is equal to y2 times y1 a raised to power minus 1 mod p. So as an exercise, I am giving you, verify these encryption and decryption rules are correct, right? So when you actually compute these things, so you can substitute these values of y1 and y2 and compute that you are getting the the actual x. So encryption decryption works. Let me give you an example here. Example, small example, p is equal to 2579, alpha is equal to 2, order of alpha is equal to p minus 1, a is equal to say 765, beta is equal to 2 raised to power 765 mod 2579 is equal to 949. Suppose x is 1299 and suppose k is equal to, k is randomly chosen 853 here. So y1 is 2 raised to power 853 mod 2579 turns out to be 435, and y2 is equal to 1299 times 949 raised to power 853 mod 2579 is nothing but 2396. All calculations you can do. So Bob receives the pair 435, comma, this one and this one, 2396. This is your y1, y2. Then he computes x is equal to 2396 times 435 raised to power 765 inverse turns out to be 1299, the plain text, right? This is a simple example. All the calculations I think you can. Okay, so I think we are ready to now give you the idea of elliptic curve. So basically, as I mentioned, it's the most beautiful thing. Ultimately, what we are doing, we are solving certain equations. Okay, so let me give you one equation here and ask you how will you solve this equation. Y square is equal to x cube plus ax plus b. A, B are suppose they are real numbers. Question is how will you solve? Any idea in the class? The equations you are doing mastering, right? All those competitive programmers, where are those? How will you write a computer program to find the solution? Any idea, from you? Calculus तो पढ़ा होगा, yes. But actually x is a real number, right? So how many values you will put? जेई तो दिया है ना, उसमें इस तरह के क्वेश्चंस नहीं पूछते, राइट? इक्वेशन कैसे सॉल्व करेंगे? ये तो हाई स्कूल का क्वेश्चन है ना, इट्स वेरी सिंपल हाई स्कूल क्वेश्चन. How will you solve y square is equal to x cube plus ax plus b? I think in IIT JEE in coaching you might have heard, अगर कुछ काम नहीं करता है you can plot. Plot तो कर ही सकते हो ना, right? So basically plot the curve and see where they are intersecting, right? And those points will be the solutions. So any guess? मैंने hint दे दिया, plot करके तो solution होगा, right? So how do we do that? So I love this equation basically. It's very beautiful. Because you see, so my job is, so A and B are reals and complex. There are two books actually on this by Silverman. You can call it Arithmetic of Elliptic Curves. I call it Beauty of Elliptic Curves, 2 volumes. You can enjoy that book. Talk about various beautiful things about these curves. Now, when you take A and B over finite field, FQ, it is much more beautiful, right? Over finite fields, it's much more beautiful. And the crypto system is based on finite field only, not real so complex, right? That work is done. So I go, but further, okay, now A and B are over integer modulo n. Then what will happen? It's much more difficult, not difficult, more beautiful, right? So more beauty will come when you move it to Zn, right? Integer modulo n. So I think you can think of somebody who is interested in doing something here. They can contact me because now we have obtained some new results. I will show you some beautiful things. Essentially, how do we solve? Over finite cases, how will you do it? By the way, over finite case, suppose over finite field, suppose I take it integer modulo 2, how will you solve? It is a very simple thing. A and B are over Z2, right? Then how will you solve? Now, if A and B are over Z2, so we know that There will be a certain number of equations. 4 equations will be there, right? And sometime you see, just like that, in the quadratic equation, there are cases, right? You can make different cases here when the solution will be, when it will not be, and all kind of things, analysis. This is already done by so many people. And so they call it a quantity known as discriminant. If discriminant is non-singular, is not equal to 0, we call it non-singular curve, right? So those things have been studied. Okay, let me describe those things for you. So actually, discriminant is this quantity 4a cube plus 27b square. And how to compute, how to come up with these things, I am not going to do the details, but I am telling you because it's a very elementary class about this. But if there is a class on elliptic curves, we can talk more about it, how to compute these things. But if you want to know more details, you can always look at this book by Silverman, Arithmetic of Elliptic Curves, 2 volumes, thick volumes. You will enjoy. Okay. So we are looking at the case when this quantity is non-zero actually. Okay. So a non-singular elliptic curve is a set of points E consisting of points x comma y in R square such that y square is equal to x cube plus ax plus b. So I'm putting this additional condition. Why that condition is there? Actually, when you try, that's why I'm saying that you should try. Use your IIT JEE techniques and see when the solution is possible, when the solution is not possible, all those kind of analysis of this equation, right? Just plot. And these days you have Chat GPT, right? So it will help you. So, right? Just type elliptic curves and see what it gives you. By the I have not tried Chat GPT, by the way, but I know that Wolfram Alpha, Wolfram has developed Mathematica, right? So he has developed a engine known as Wolfram Alpha. I don't know whether if you are using iPhone, earlier Siri used to give you answers from Wolfram Alpha. I'm sure it must be using something now. So basically, you can try some of these things there and see the behavior of the curve. So I think I'll take an example and see the plot. So basically, this solution, all those points, and we also need another point known as point at infinity. Together, they form a group with respect to addition. The addition is defined in a certain manner, which I'm going to talk about. Before that, let me plot the curve actually for a special case. So it is y square is equal to x cube minus 4x. So I'm not very good artist, but I'll at least try to make it for you 0, 1, 2, 3, 4, 5, and so on. Minus 1, minus 2, minus 3. Something like this and something like this. This is a kind of plot when you see. Okay. So now, so points are actually on these curves. So now how do you define addition? So you take 2 points on this curve. So basically what you do, take any 2 points P and Q on this curve and draw a line. Okay. And then that line will intersect at third point. Okay. Call it, say, R prime. So, or R. So then there are 3 points P, Q, R on the curve. So addition of P and Q is defined that it's like you take R prime and take the mirror image of R prime. And that becomes the third point, which is the addition of first 2. Okay, that is a geometrical way. How do you describe the addition? And then of course you can calculate the by equation of the line and so on and so forth. You can actually find a formula for this point, so which I am going to do it for you. So I should mention why this condition was there. This condition was there. I should mention to you the equation x cube plus ax plus b has three distinct roots. Maybe in R or C. If and only if 4a cube plus 27b square is not equal to 0. So I think I invite you to prove this fact. I think this much you can prove. So this equation has three distinct roots. By the way, how do you solve a cubic equation? JEE exam में पढ़ाया है, right? Cubic? No? Cardan's cubic solution, you know? Cardan's cubic solution, who knows in the class? No, no one? See, if you, I mean, equation solving is very, very important. And I think you know that Sridhar Char gave you degree 2, Cardan's cubic solution is degree 3, and there is a degree 4. And why we cannot find a formula for degree 5? There is a reason. 5 onwards, we don't have a formula for computing the roots. It's a very basic thing. So this equation has three distinct roots if and only this quantity is non-zero. So if this quantity is 0, we call the curve as singular curve. So you can actually classify. So right now, as I mentioned, we are looking at the case when a and b are over integer modulo n, and we are trying to classify these equations first of all. Before developing the crypto system, you need to classify. So we have already done a lot of work in this area. So some of your last year, 2 students from your last year class, they started working on it in elliptic curves, and they have done some classification actually. Anyway, so okay, so let me now describe this group here. So E is our non-singular curve. So we know that what is the condition? Non-singular curve. So I am saying that E with respect to addition is an abelian group. What a beauty actually, right? So now, how do we define addition? First of all, so in fact, there are different cases. So first of all, I define a point O, which is called as point at infinity. Without giving much details, I am just writing that this point is such that for every P in E, P plus O is equal to O plus P is equal to P. Right? Second, if I take 2 points P and Q in E is no, you know what is this set, right? E is the collection of these points, right? E is this set. Okay. So if we take P to be a point x1 comma y1 and Q to be a point x2 comma y2. So first case 1, this is a Russian notation actually. 1 raised to power 0 means 1, just some section. When x1 is not equal to x2. In this, so this is case 1. Case 2, when x1 is equal to x2 and y1 is equal to minus of y2. And case 3, I mean, this is all bad. X1 is not equal to x2. Case 2, x1 is equal to x2 and y1 is equal to minus y2. And case 3, x1 is equal to x2 and y1 is equal to y2. So these are 3 cases, and I am going to, the formula is a little bit different in all the 3 cases. So first of all, I am going to give you the formula for case 1, when x1 and x2 are distinct. Okay. So here is case 1. So L is a line passing through P and Q. So if L intersects in another point R prime on the curve, as I mentioned, so if you draw a line, you know, here if you draw a line, say, suppose this is P, this is Q, right? So you can always draw a line and it will hit anywhere else here. This is your point R prime, okay? Something like that. So when you draw a line, take 2 points, it will intersect another point on the curve, right? Now we reflect R prime in the x-axis, okay? And we get a point R. Actually, P plus Q is equal to this R. Can you tell me now how do you find this formula? P is x1 comma y, x1 comma y1, Q is x2 comma y2. You see R, you can call it x3 comma y3 or whatever. Can you find the formula in terms of accelerator? You saw the geometric operation, right? P and Q are 2 points on the line. Distinct, case 1, x1 is not equal to x2. You draw the line, it will hit another point. Take the reflection of that point with respect to x-axis, that is your R. So you can actually find a formula for it, right? So equation of the line is, I'm just doing some calculations for you. Equation of the line L is y is equal to lambda x plus v. It's very difficult. Lambda x plus v. V is the intercept, right? Slope lambda is equal to y2 minus y1 divided by x2 minus x1. And we know that v is equal to y1 minus lambda times x1 is equal to y2 minus lambda times x2. Do you agree with this? This is a simple calculation. High school mathematics, right? You can find these things. Next. Now I need to find points basically in the, we are looking at E intersection L, right? How do we find that point? I'm going to substitute the value of y, this value of y. We know that the equation of the curve is this. Y square is equal to xu plus ax plus b. So I can substitute the value of y here and see what happens. So this will be lambda x plus v whole square is equal to x cube plus ax plus b. So this will give us a quadratic equation in x, right? And we can solve for x, right? So here, so the equation can be written as x cube minus lambda square x square plus a minus 2 lambda v x plus b minus v square 0. So now we know that P and Q are 2 points on the curve, right? That means actually, you know, we know that x1 and x2 are solution of this equation. I can call it star. This is star equation, right? So roots of this equation are actually, you know, x coordinate of points in E intersection L. Okay, so whatever is the, you know, x axis thing. So if x1 and x2 are real, or real, x3 is also real, and some of the roots are x1 plus x2 plus x3 is equal to lambda square. So x3 is equal to lambda square minus x1 minus x2. So we found the first coordinate x3. X3 is the x coordinate of of r prime. So y coordinate of r prime is, we know that, of r prime is minus y3. So y coordinate of r is y3. Okay. Now the slope of the line is determined by any 2 points on the line, right? So I can, so slope of the line, L can be determined by any 2 points on the line, right? So if we take x1, y1 as 1 point on this line, and here the other one is, which we just described, x3 comma minus y3, that reflection one, right, are these 2 points. So lambda will be minus y3 minus y1 divided by x3 minus x1. Therefore y3 is nothing but lambda times x1 minus x3 minus y1. So formula becomes for p plus q. So we have found the value of y3 here, right? So basically x1 plus, sorry, x1 y1 plus x2 y2 is equal to x3 y3, where x3 turns out to be lambda square minus x1 minus x2, and y3 turns out to be lambda times x1 minus x3 minus y1. Here this lambda is equal to y2 minus y1 divided by x2 minus x1. I think at least this much. So it's just idea is simple, but the calculations you can compute. So you know how to addition defined when x1 and x2 are distinct. So other two cases I'm going to do in the next class. How actually you can find the other 2 cases. Then I'll give you an example how to find these points. And actually there is a famous when you convert this problem into finite field, there is a bound on the number of points on this curve known as Hasfell bound. Beautiful bound, and the proof is also simple. It's a thick book, you can look at it, but it's a very beautiful thing. Anyway, thanks a lot. We'll meet next class tomorrow.